Hello, everybody. This is Mr. Fasoni. Today, we're going to go through some example problems for chapter 6.5. We've already gone through the whole lecture where we've talked about the rules of logarithms, how we can expand and condense logarithms. And then we're also going to do some change of base and a few kind of word problems that culminate all the stuff that we've learned about logarithms. Let's go ahead and start off. We're going to be doing expanding logarithms first. So just remember, we can use these the product property, the quotient property, and the power property, which are the three properties of logarithms to, when we expand, we go from the left to the right. We're going from something a little bit more complex to something that has simpler terms, but more terms in the case of both the product and the quotient property. And then the power property, we simplify things a little bit by getting rid of an exponent. We end up moving it out front and it creates a multiplier. In all these cases, we're going from a higher order operation, like in product property, we're going from multiplication, m times n, to an addition of the logarithms. With the quotient property, we're going from a division, m divided by n, to a subtraction of the logarithms. And then finally, like I said, in the power property, we're going from the exponent in the value that's inside the logarithm to a multiplication of the logarithm. So that n is actually outside of the logarithm operation at that point. All right, so we're going to be using these properties. And remember, when we are expanding, what we want to do first is we want to break it up into as many pieces as possible first by using the product and quotient properties. And then once we've done that, we're going to come back to the power property and simplify any individual terms that can't be split out anymore by using the first two properties, but can be simplified within the individual properties. So we'll be doing product and quotient property first, and then finally the power property second, or last, I guess. Let's go ahead and just kind of rip through these. There's 4 examples here for expanding. The first one is log base 8 of 3x. So 3x is the value that's inside the logarithm. I'm taking what power of 8 could get me to 3x. I can use my properties. If I look at this, inside the parentheses, I've technically got a product. I've got the number 3 multiplied by the number x. So I'm going to use the product property, I keep stumbling over my words, to split this into 2 separate logarithms. They're both going to be a base 8 still. The base stays the same. So it's going to be log 8 of 3 plus log base 8 of x. And we're officially done with that one. They go very, very quick. In fact, I'm going to move real quick and expand this. Otherwise, I'm going to take up too much space. All right, so that was the first one. Second one, natural log of 3x to the 4th power. Again, this is the whole value that's being put into the natural log operation. And again, we've got a product property between 3 and x to the 4th power. 3 is being multiplied by x to the 4th. So I'm going to go ahead and rewrite that one. Again, it's going to go pretty quick. It's going to be the natural log of 3, that's my first term, plus the natural log of x to the 4th. So I use the product property to split that. Now, what happens here is I've split it into 2 pieces. Each piece is a little bit more simple than the previous original piece. And I'm actually done with the first term. I can't do anything with that. But the second term, I can actually break down a little farther. I'm going to rewrite this using the power property. So I split it using the product property. I'm going to rewrite it using the power property. That means I'm going to bring this 4 out in front. It's going to be 4 times the natural log of x. And then the other piece I just bring down. Natural log. I should leave purple for a second there. So it becomes natural log of 3 plus 4 times natural log of x. And again, I've now fully expanded this one. All right, I'm clearly not doing a good job with my space management here. Let's see if I can do some more down here. Natural log of 6x squared over y to the fourth. And the last one is going to be log base 5 of the third root of x squared y. So this one here, the natural log of 6x squared over y to the fourth, we're doing a division here. So we're going to use the quotient property to rewrite this by breaking it into two pieces. In this case, with the quotient property, the two pieces are the numerator and the denominator. I should use a different color than pink. That doesn't really show up very well against the purple. Let's go blue. So this breaks into two pieces. Both of them are natural log, because that's the base we started with. Natural log of 6x squared. And then it's going to be a subtraction, because quotient property turns a division into a subtraction of logarithms. So minus the natural log of y to the fourth power. All right. So as far as properties go, on this first one, I can still continue to break it into pieces by using the product property. So I'm going to use the product property here. And the second one, I can't break it into individual pieces anymore, but I can use the power property. I'm going to hold off on the power property until the next step, because I will actually have two power properties on that next step. So it's going to be the product property for natural log of 6x squared. If I want to look at these as individual pieces, one of my pieces is 6, and the other piece is x squared. So I'm going to break that into two separate natural logs. Natural log of 6. Oh, wrong color. Natural log of 6 plus, because it's the product property, the natural log of x squared. And I'm just going to bring down the last piece, minus the natural log of y to the fourth. All right, so now I've used product and quotient property as much as I can. I've broken it into as many pieces as possible. The last part is I'm going to use the power property. I'm going to use the power property twice on both of these terms. I'm just going to write pow. Actually, no, I'm going to write power. Kind of. So we use the power property on both of these. The first one I can't really do anything with, so I'm just going to bring it down. Natural log of 6. I'm just going to keep the color all purple now, because there's not really any change here. And then I'm going to be adding, well, on the power property, I'm bringing these exponents forward on their individual pieces. So the 2 is going to go out front, and then the rest of it is going to come down. 2 times the natural log of x minus, and then I'm going to bring out the 4, minus 4 times the natural log of y. And now I fully expanded that statement. All right, let's do the last one. This one's actually kind of a challenge problem. We're not going to have any questions that are like this specifically on the test, but I think it's good to see. So it's the natural log, oh no, I'm sorry, not natural log, the log base 5 of the third root of x squared times y. Okay, so remember, the third root, I can rewrite that as an exponent. So I'm going to go ahead and just do a rewrite really quick. Got log base 5 of x squared y to the 1/3 power. So this is kind of an oddball problem. In this problem, I will actually have to use the power property first, because this product is inside this exponent. So what I'm going to do is I'm going to use the power property on this. I'm going to bring this 1/3 out in front. It's going to become 1/3 log base 5 of x squared y. Okay, well, I'm going to actually do this to kind of organize my thinking. This is 1/3 times log base 5 of x squared y. So inside these brackets, now I'm going to use my product property. So this product property is going to end up splitting this into two pieces. In this case, my pieces are, again, x squared and y. So I'm going to rewrite. I'm going to get log base 5 of x squared plus log base 5 of y. Now remember, this is all in parentheses, so technically I still have that 1/3 hanging out here. And we'll get to that in a second. Got one more thing to do before I get there. I'm going to now use the power property again on this x squared. So what ends up happening now is I get log base 5 of, well, I have an x here, and the squared ends up going out. So it actually becomes 2 times log base 5 of x plus log base 5 of y. Let's not forget, though, I still have this 1/3 hanging out on the outside. I could leave it like this, but if I wanted to simplify and multiply everything through, I would then distribute that 1/3 to both of the terms. And I'd end up getting 1/3 times 2 is 2/3. And then I got log base 5 of x plus 1/3 times log base 5 of y. And now I've got everything expanded as far as I can and simplified as much as I can, and I'm done. That was expansion. That's one direction. These next 4 problems are going to be about compression. Compression is just going the opposite direction. If I've got an addition of logarithms, I can turn it into a product of values inside a logarithm. If I've got a subtraction of logarithms, I can turn it into a quotient expressed inside the logarithm. And then finally, if I'm multiplying a log by some number, I can actually put that number back inside the logarithm as a power of whatever that value m is. So again, I'm going to kind of go quickly through these. I'm going to go ahead and rewrite them because I know I'm going to run out of room. So let's go quickly. I've got log base 5 of 4 plus 1/3 log base 5 of x. And let's do 6 ln 2 minus 4 ln y. 5 natural log of 2 plus 7 natural log of x plus 4 natural log of y. And then finally, well, I'll come back to that last one. Okay, so let's condense some stuff. So I'm going to be putting things back together. When I'm putting things back together, I'm actually going to do the power property first. And then after I've done power property as much as I can, then I'll do the product or quotient properties. So if I look at these, if I'm looking for a power property, in this first problem, the second term looks like a power property. It's 1/3 times log base 5 of x. So what I'm going to do is I'm going to rewrite that. Again, this is the power property. I'm going from right to left. It becomes log base 5 of x to the 1/3. I've taken that power. I guess I should rewrite this with this kind of light gray or white color. So 1/3 becomes the power there on this second term. And I'm just going to bring down the first term. No difference here yet. All right, next up, I'm going to use the product property. So this product property can now put together these two values that are being added. I'm using the product property because I've got an addition. So this just becomes multiplication between the two terms. Term 1 is 4, and term 2 is x to the 1/3 power. So when I rewrite this, now I have just a single term, log base 5 of 4 times x to the 1/3. I can put that in parentheses just to show that this is all one term together. So I'm taking log base 5 of 4x to the 1/3 power. All right, let's continue. The second one is 6 natural log of 2 minus 4 natural log of y. On this one, I actually have two power properties to start. So I'm going to go ahead and clean these up by taking the numbers out front and putting them into exponents inside the logarithm itself. So I have natural log of 2 to the 6th power minus natural log of y to the 4th power. Now, in these cases where I've got numbers to powers, what I can do is I can simplify this. 2 to the 6th power, I can just take 2 to the 6th, which is actually 64. So I'm just going to rewrite 2 to the 6th as 64. So now I've got the natural log of 64 minus the natural log of y to the 4th power. And now I'm ready to finish this up. I've got a subtraction, so this is going to be the quotient property. And to put this together, I'm going to have, again, two terms. 64 is going to be my numerator, and y to the 4th power is going to be my denominator. So that I can rewrite this as natural log of 64 divided by y to the 4th power. And again, I can put this in parentheses just to show what's going on. And now I'm done. So condensing is all about putting it back together and making it kind of more and more complex in the process. All right, I'm going to kind of speed this up on this one. Same idea as the previous. We've got the power property 3 times. So 5 natural log of 2, well, that's going to become the natural log of 2 to the 5th plus 7 natural log of x becomes natural log of x to the 7th. And 4 natural log of y becomes the natural log of y to the 4th. Again, I'm going to clean up this 2 to the 5th. I'm just going to turn it into 32 because that's what 2 to the 5th power is. Bring down everything else. I'm going to get rid of the color coding to save some time. So I've got natural log of 32 plus natural log of x to the 7th plus natural log of y to the 4th. This now becomes just a series of product properties. I'm going to go left to right. I'm going to rewrite this. It's going to be the natural log of 32 times x to the 7th. 32 is my first term. X to the 7th is my second term. And then I'm going to bring down the third term plus natural log of y to the 4th. So now I've got another product property that I'm going to be doing because I have another addition. So I've got product, and again, I'm just going to end up multiplying everything together. It becomes natural log of 32 x to the 7th, y to the 4th. In this case, my first term is 32x to the 7th, and my second term is y to the 4th. And again, I can put this in parentheses just to kind of show what's going on. And I'm done. All right, the last one looked like it was a little bit tougher. Let's go ahead and grab that again. Log base 3 of 4 plus 2 log base 3 of a half and log base 3 of x. Okay. So log base 3 of 4 plus 2 log base 3 of 1/2 plus, what was it, log base 3 of x? Okay. It actually isn't that tough. If I'm looking at this, I've got a power property in the middle. So I'm going to rewrite this. Again, my 2 is going to become a power out here. So it's going to be log base 3 of 1/2 to the second power. And then I'm going to bring down the other pieces. log base 3 of 1/2 to the second power, I can evaluate that 1/2 to the second power. 1/2 squared just becomes 1/4. So I'm just going to do a quick rewrite again. And now I've got 3 terms that are all being added together. This just becomes product property 2 times in a row again. So product property of the first 2 terms, 4 is my first term and 1/4 is my second term. So I'm going to multiply those together inside the logarithm. It becomes log base 3 of 1, because 4 times 1/4 is 1. I'll write those out actually. 4 times 1/4 plus log base 3 of x. All right, so very quickly, 4 times 1/4, like I said, becomes 1. So this is really just log base 3 of 1 plus log base 3 of x. And then finally, the last thing I need to do is the product property. I'll actually make a comment on this before, after I finish it following the normal method. Product property, again, I'm going to have 2 terms. 1 is one of my terms and x is another. So I get log base 3 of 1 times x, which we all know is just going to end up being x inside the parentheses here, log base 3 of x. Now, one thing I wanted to note, if you are paying attention to your logs, you can catch this. Log base 3 of 1, remember logarithm statement, log base 3 of 1 is just asking 3 to what power? I have an x there. 3 to the x power equals 1. Well, if I wanted to figure out what that x is, anything to what power will give us 1? Well, anything to the 0 power will give us 1. That means that this value here in this box is equal to 0. I'm sorry, is equal to 0. So what technically I could do, I could rewrite this as 0 plus log base 3 of x. And at that point, we don't need the 0, and there's my answer again, log base 3 of x. So kind of 2 different ways to look at that. All right. So let's go ahead now and hop over to the change of base rule. Remember, the change of base rule is what allows us to solve any logarithm with any base by using our calculators and converting a logarithm into a basically a division problem or a fraction that involves 2 logarithms that are either common logs or natural logs. So this is very procedural. I'm going to zoom in here. So I've got these 4 logarithms to solve. I'm going to solve them all just kind of back to back. Remember, these logarithms are all in the form of log base c of a. And I can rewrite them as either log of a over log of c, or I can rewrite it as natural log of a over natural log of c. Either way is fine. So if I want to look at this, if I want to find my my a values, well, my a values are going to be the target value that I'm trying to reach with these logarithms. And then my c values are going to be all my bases for each of these logarithms. I think it's very quick. I'm basically writing out some fractions. Log of 13 over log of 5. On this one, I'll stagger these so I can fit them better. Actually, let's do this instead. Log of 13 over log of 5. The second one is going to be log of 22 over log of 8. These next 2 I'll actually do using natural log instead. Natural log of 28 over natural log of 2. And finally, natural log of 9/40 over natural log of 3. The a value, the larger value to the right in orange, that goes in the numerator. The c value, which is the base on the logarithm, goes into the denominator. At this point, it's all calculator work. So on the first one, I'm going to do 13. I'm going to take the log. Log of 13 gives me that. I'm going to divide that, hit the divide key by 5 log, and then I'm going to hit equals. So on this very first one, log base 5 of 13 is 1.594 because I'm going to round it. And I'm done with that one. I can check it really quick to make sure I'm sane. 5 to the 1.594. Oh, wrote that wrong. 5 to the 1.594 power gives me 13.006. So it does check out. All right, let's step through these pretty quickly. Log of 22 divided by log of 8 equals 1.486. This is the same. 8 to the 1.486 power will give me 22. Same way it works with natural logs. Natural log of 28 divided by the natural log of 2 gives me, oops, it equals 4.807. So 2, which is my base, to the 4.807 power is going to give me 28. And that makes sense if you really think about what you know about your powers of 2. We know that 2 to the 4th power is equal to 16, and we know that 2 to the 5th power is equal to 32. So if I'm trying to hit 28, 28 is between 16 and 32. So similarly, the exponent that I'm going to need is going to be between 4 and 5. All right, last one. This one has a fraction, but don't let that freak you out. I'm going to just figure out what 9/40 is. 9 divided by 40. And then I'm going to take the natural log, move over here, take the natural log of 9/40. And I'm going to divide it by the natural log of 3. And I get negative 1.358. So again, this is saying that 3 to the negative 1.358 power should be approximately 9/40, which was 0.225. And again, I can check that if I want. 3 to the 1.358 negative power equals negative, or 0.2249. So basically 0.225. That little rounding that we did on the exponent doesn't really cause too much of a change. All right, so that's change of base. So now I'm going to kind of switch gears, and we're going to go through some problems where we are solving things a little bit differently. So in chapter 6.2, when we were dealing with exponential functions, for instance, when I was dealing with a function like, let's see here, losing my train of thought here. An exponential function that looks like y equals a times b to the x, or we could have y equals a times e to the rt power, or any of the financial ones, compound interest ones. Regardless of what we had, most of the time we had, we were given the base, we were given the rate, we were given the starting values, and we were given either the time or the number of iterations that we want to run through, but we did not have the y value. And we calculated the y value by plugging in all the values and then doing some math. So in this case, what we're going to have, instead of having all the inputs and just figuring out the output, we're going to have like a different set of things. We might have the output, the initial value, and the base, but we don't have the exponent. or we have the output, the initial value, the rate, but we don't have the time. So we're gonna have to do a little bit different problem solving, because instead of just evaluating, we're going to have to actually do some inverse operations to get a single value by itself. So let's get going on this. This one's about the radioactive decay. So we've got 100 grams of radium that are stored in a container. We've got some equation here. The amount R in grams of radium present after T years can be modeled by R equals 100 times e to the negative 0.00043 T. And what we're trying to figure out is after how many years will only 5 grams of the radium be present? So our equation looks like this. And normally we would get a time. We'd say like, okay, well, you have 100 grams and after 20 years, how much do you have left, right? That's how we usually do this problem solving. You know, maybe they put 20 years in there or something. But in this case, we're not given the amount of years, but we are given the final amount. We want to know after how many years will only 5 grams be left. So I'm going to rewrite this with that 5 grams in place. So I've got 5 equals 100 times e to the negative 0.00043 t. So what I want to do is get t by itself. That's my goal, is to get this guy right here by itself, because I'm solving for t. Okay, but it's hiding up in an exponent and there's all this other stuff around. So what I'm going to do is I'm just going to start doing inverse operations. If I'm looking at this expression is 100 times e to the negative 0.00043 t power. Well, remember, when we're solving for a value using inverse operations, think about our order of operations. When I want to evaluate and find an answer, I'm going from left to right. I'm going in the normal order. But when I want to solve for a specific value, I'm using inverse operations. And technically what I'm doing is I'm going in the inverse direction. So I'm using inverse operations and I'm going in the reverse order. So in other words, before I can address, or look at this statement again, on the left side of the equation, I've got two things happening really. I've got a multiplication happening. Got really bad handwriting happening too. And then inside this exponent, the e to the whatever, I've got an exponent, right? In an exponent, I've got an exponent. That was not very well described. But I've got two different operations happening. I'm multiplying e to the blah, 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 blah power. But before I even multiply it, if I was evaluating it, I would take the exponent first. But my goal is to get t by itself, so I'm actually going to go in reverse order. I'm going to clean this up by getting rid of that multiplication first. All right? Cool. So again, I'm trying to get t by itself. So the very first thing I'm going to do is I'm going to divide both sides of the equation by 100. And what that does, the left side of the equation becomes 0.05. And then the right side of the equation now just got a little simpler. It's equal to e to the negative 0.00043 t power. Okay. So I've done an inverse operation of multiplication. I did division, right? That's the inverse. Next up, what I have to do is the inverse operation of the exponent. Well, to inverse the exponent, I'm going to take the logarithm on both sides of the equation. Let's use a lighter color there. I'm going to do the natural log on both sides. The reason I'm using the natural log is because my base in this exponent is e, and the natural log is the log base e. So I'm taking the natural log on both sides of the equation. Well, the natural log, if I'm taking the natural log of something, a power of e, what happens is the natural log and the base end up canceling out. That was a property from chapter 6.3. It's an inverse property of logarithms, and I get negative 0.00043t on the right side of the equation. The left side of the equation is still the natural log of 0.05. All right, we're almost there. I've got one more thing to do to get t by itself. And in this case, it is just dividing both sides of the equation again by 0.00043, or negative 0.00043. Those cancel on the right, and on the left side, I have kind of this messy statement. I'm just going to write it all in one color now. It's the natural log of 0.05 over negative 0.00043. That's going to equal t. Well, at this point, all I have to do on the right side of the equation is evaluate. So let's go to our trusty calculator. 0.05, take the natural log of it, divide that number by 0.00043, but it's negative, so make sure to turn it to negative, hit the equal sign, and I get 6,966.8 years. I'm going to round that up to the nearest year, and it's going to be 6,900, what was it? 67 is roughly equal to t. So in other words, it's going to take 6,967 years for this radioactive radium to decay down to only being 5 grams. But we've now done it. We've gotten t by itself. All right, let's jump forward. This one's actually an inverse with a logarithm. So the apparent magnitude of a star is a measure of the brightness of the star as it appears to observers on Earth. The apparent magnitude m of the dimmest star that can be seen with a telescope is the following equation. M equals 5 times log d plus 2, where d is the diameter in millimeters of the telescope's objective lens. So what is the diameter of the objective lens of a telescope that can reveal stars with a magnitude of 12? Okay, so let's just put this all together. My equation I have is m equals 5 times log of d plus 2. And the value that they gave us 12 for m. Okay, so I'm trying to solve for d. This time I'm trying to find the diameter. But there's a bunch of stuff that's attached to that statement on the right that I need to move to the left or get rid of by using inverse operations. So I'm going to use my order of operations in reverse again. Well, the lowest thing on the order of operations is addition and subtraction. So I'm going to subtract to get rid of this addition. Subtract 2 from both sides of the equation. That's step 1. Now I've got 10 equals 5 times log of d. Okay. Next up, I've got a multiplication. 5 times log d. Well, that's easily gotten rid of by dividing by 5 on both sides. 5's go away. 10 divided by 5 becomes 2. So I have 2 equals log of d. Okay. Well, we had, again, a different inverse operation. If I want to get rid of a logarithm, I'm just going to stick that logarithm into an exponent with the same base. Well, notice I don't have a base here. There's usually a base right there. Well, if I have just the word log, that means I'm technically in base 10. So what I'm going to do is I'm going to use that base on both sides of the equation. I'm going to take 10 to the second power. So I'm basically taking the left side of the equation as an exponent and the right side of the equation as an exponent. 10 to the second power is going to be equal to 10 to the, this is the weird part, log base 10 power of d. But what happens because of these rules from 6.3, what happens is this 10 to the log 10 power, those statements destroy each other or cancel each other out. And what I'm left with on the right side of the equation is just that value d. So I've got 10 squared equals d. Well, at this point, I just evaluate the left side. 100 equals d. And now I've got my value. That one was much quicker. So the diameter of an objective lens of a telescope that can reveal stars of the magnitude 12 is 100. I guess that's 100 millimeters. There we go. All right, last one. This is all about interest. And this is compounded interest, not continuously compounded interest, but interest that's compounded on a regular interval. So remember, the equation for this type of interest is my amount is equal to my principal times 1 plus my rate divided by the number of compounds to the number of compounds times the number of years. That's my equation. So if I deposit $100 into an account that pays 6% interest, how long will it take the balance to reach 1,000 for each frequency of compounding? Okay, I'm going to do maybe just a couple of these, but it's really the same equation over and over. I'll do quarterly and daily. Oh, there's a continuously here too. Let's do daily and continuously. So I'm going to use the equation on the left for daily, and then continuously it's going to be the A equals P times E to the RT power. Okay, so let's do daily first. Let's plug in all the stuff that I know. So I want to reach, with daily, I want to reach $1,000. That's my A amount at the end. I'm starting with $100. And I'm doing 1 plus my rate. Remember, if I have a 6% rate, that's equivalent to 0.06 in decimal. And then daily, let's assume it's not a leap year, so divided by 365. And I'm going to take it to the 365 T power. Okay, so I'm going to use some inverse operations. This is going to kind of go fast. First thing I'm going to do is divide by 100. After I divide by 100, I'm left with 10 on the left side of the equation. Right side of the equation is a little bit simpler. It's 1 plus 0.06 divided by 365, all to the 365 T. Okay, so this is a little bit messy. What I can do is just divide this out. Let me divide out the rate, 0.06 divided by 365. I'm going to add 1 to it. That's going to give me a very long decimal, or very close to 1 decimal. So what I'm going to do, this is kind of a tough one actually. Let's see if I can express this a little bit differently. Let's take let's try using our properties that we used when we expanded a logarithm. So this is going to be a little bit different because it's such a messy decimal. So let's go ahead and try this. I'm going to take the logarithm, common log on both sides. Okay, I'm going to do some trickery with expanding on the right side here. I've got an exponent. And take this exponent, I'm going to put it out front using the power property. 365t times log of 1 plus 0.06 over 365 is the same as log of 10. Well, log of 10, log base 10 of 10 is just going to be 1. Right? So I've got 1 equals 365t times log of 1 plus 0.006 over 365. This is kind of a mess, but what I can do now is I can divide by 365 on both sides. That cancels. So now what I have, and this is hard to get to an exact value, but I have 1 over 365 equals t times log of 1 plus 0.06 over 365. Still kind of strange, but follow me on this. What I'm going to do now is I'm going to rewrite this 1 as a 365 over 365. And I'm going to add that to 0.06 over 365. This is all inside the parentheses. Everything else is still coming down. This is a tough question. I didn't do it beforehand, so I'm kind of figuring it out as I go along. What I'm going to do now is I'm going to rewrite this parentheses. 365.06 over 365. Remember, this t is still multiplying everything. Okay. What's interesting here is I'm going to just kind of remove, I'm going to exclude t for a second. I've got a quotient property right here. So this becomes t times log of 365.06 minus log of 365. So let's calculate that part out. Actually, before I even do that, I'm going to bring everything else down, 1 over 365. The last thing I'm going to do to get t by itself is I'm actually going to divide by this big statement. Log of 365.06 minus log of 365. I'm going to do that on both sides of the equation. I know I'm kind of going fast. That's what the video is for. So I have 1 over 365, that was still on the left, divided by log of 365.06 minus log of 365. What a giant, colossal mess. Equals t. Because remember, these guys both canceled. Boom, boom. We're left with t. So now all I have to do is evaluate this. It's a giant mess, but we can do it. 1 divided by 365, that's my numerator, divided by, I'm going to put this in parentheses because it's such a mess, 365.06 log minus 365 log, and then I'm going to close the parentheses, and then I'm going to hit the enter sign. And I get 38.3795, so 38.38 years. So that's how many years it'll take me to get to $1,000 compounding daily at 6% interest if I start with $100. That's pretty crazy. The last one, continuously, is not quite as bad. Again, my goal value is 1,000. It's going to be equal to 100 times e to the 0.06 t. If I do inverse operations, it goes pretty quickly. Divide by 100 on both sides. I get 10 equals e to the 0.06 t. I can take the natural log on both sides. Natural log of 10 is going to be equal to natural log of e to the 0.06 t power. I apologize for the dog barking in the background. These cancel out. I get the natural log of 10 is equal to 0.06 times t. Last thing I have to do is, again, divide by 0.06 on both sides of the equation. And I get the natural log of 10 divided by 0.06 is equal to t. Calculate that out. 10 natural log divided by 0.06 gives me 38.376 years, which is right in line with the previous one, which was 38.38 years. So it's just slightly faster if I'm continuously compounding. All right, that's it. I'm out of time, so I'm going to stop here. If you have any questions, let me know.